Jonathan, we finally
Patrick,
made
it's
it.
great to be here with you.
Yeah, are you ready for this? Because we put out a pretty tempting title. We're going to lure people in. Like, your database
Yeah, I
doesn't
mean
have to suck.
there's very few things more interesting right now than vector databases, so that's why I'm here.
Yeah, so when I promoted this video, I said, Jonathan's going beast mode, which is not that's not an understatement. You've really so you and I have known each other for a really long time. And which is I also don't want to turn this into like a get off my lawn moment, but we kind of can. Because I think about like what I say, like, oh, your vector database doesn't have to suck. You and I back in the day were talking, we were like the NoSQL upstart people, we're out there like use Cassandra
That's right.
and
Like we were out there saying, scaling doesn't have to suck. Being downtime tolerant doesn't have to suck. Yeah, there's a whole bunch of things that you should expect your database to do. And a lot of those have become table stakes now, but another one is vector search, and that's table stakes in 2023.
Yeah, and we were getting like so much shade from like the oracles, the neckbeard people from Oracle, like use a real database, and look at us now. Cassandra's been on a real tear for the last like 10 years, and it's a very mature database now. Wouldn't you say that?
It is, yeah. And it's interesting because back 10, 13 years ago, people would say, oh, we can do all of that with Oracle. And you and to some degree, like when you're talking about CRUD operations or normal indexing, like, yeah, you can do that with Oracle. You're going to have to manually shard it at your application tier, and that's going to suck. But the actual, like, can Oracle handle this kind of query? Yeah, it can do that. The interesting thing about vector search is that it is not shaped like a problem that you can solve by throwing a B tree at it, which is what you do with Oracle and what you do with PostgreSQL. And I think that's why, I mean, not to steal your thunder here, but I think that's why
No,
PG
Steve away,
Vector
man.
sucks
Have
so
fun.
hard. Is that you're jamming this problem that doesn't fit that B tree paradigm into a relational database, and it just doesn't work. And by contrast, Cassandra's storage attached indexes are designed up front to be able to have multiple algorithms attached to them. So doing an HNSW or a disk ANN vector search on top of that storage attached index architecture is super easy and a great fit.
You've not stolen any thunder at all, and I have a bunch of questions for you. But I thought it'd be fun to start with like a really good one. It's like, this is going to be fun. I don't know if you knew that I was going to do this, but I'm going to have fun with you right now. The very first Cassandra ticket. I mean, this is just to say, like, hey, first of all, I want to make sure that everyone knows who you are, Jonathan Ellis, Mr. Cassandra from back in the day. But but here's the fun part that I'm going to do. So I put a QR link up there. You should be able to see it. It's the first Cassandra ticket. You're going to laugh when you see this. Cassandra 1. And this is what I thought was great about this ticket. It says remove support. It wasn't like support for Cassandra. No, he added delete. Like there was a database that didn't have delete. This is the first Cassandra Jira.
So. This is actually how I broke Facebook, by the way, because I'd been added as a committer to Apache Cassandra, and the Facebook guys were still deploying from trunk live. And so like over the weekend, they're instant messaging me saying, what did you do? Like everything broke. So it turns out that, I thought it looked good. Nobody reviewed it in a timely fashion. And so I just committed it. And Facebook's inbox search broke, which is what was powered by Cassandra. So we unbroke it, and then they reviewed it, and that was how it got started.
I see. This is what I was hoping for. The stories, it's like, but I also want to start out with like, hey, you've been here, you've done this. So let's talk about today. Let's talk about vectors. And so vector databases are the coolest kid right now in database stuff. There's a lot going on in all powers Gen AI, but there are problems. And I want to start out with a couple. I know you have a list in your head. I'm gonna break it up. The one that I think is the most troublesome is this problem of concurrency, which it was a shock to me that this is still a problem we're solving, but maybe you can dig into that. Like vector databases have a problem here.
Yeah, so let me tie this into what you just put up there, which is that my philosophy as an entrepreneur and as an engineer is I want to spend my time solving interesting problems. And
Mm,
almost all the time, if somebody else has already solved it, like that just makes it less interesting because like there's a known solution. And some people get excited about rewriting C++ code in Rust or whatever. And it's like, that's not me. Like, however much that makes the world a better place, perhaps, I'd rather be solving problems that nobody knows how to solve yet. And so that's what attracted me to Cassandra. Rather than like going and building something from scratch, I'm like, hey, these Facebook guys, some of whom worked on the original Dynamo paper or the original Dynamo engine, they've open sourced this really interesting database. I'd rather go contribute that and move the state of the art forward rather than spend 6 months, building something super basic. And so that was my approach to adding vector search to Cassandra as well. So I looked around and I said, who's got some good building blocks that I can use instead of reinventing the wheel? And so that brought me to Lucene. And so they've had a HNSW. I'll talk about what that means in a second. But they have a vector indexing engine that's been in production for about a year and a half now. Uh, a lot of smart people have put a lot of time into it. And so I said, hey, I should start with that rather than rolling my own from first principles. And so that is what I did, and that's what the first release of vector search in DataStax Astra, which is our hosted Cassandra, that's what that ran on was on a Lucene index. But I ran into a couple challenges with that. And by the way, yeah, like a lot of people are using Lucene. Like it's not just Elastic and Solar, but a lot of people are using Lucene for this. Um,
It
but
is it is
the
kind of an engine behind the engine for a lot of things out there.
Yeah,
Yeah.
yeah, and I mean, it's well designed for that. It's supposed to be an embeddable search engine, and it delivers. And the Lucene developers
Yeah.
are very performance oriented and very careful about backwards compatibility. So yeah, it's no wonder that they're so popular. They're the best at what they do. Uh, but in the vector space, Lucene has a couple problems, especially from the Cassandra perspective. So the first of those, just generically, not related to the vector part, but just in Lucene in general, has a kind of you could call it a micro batch design, where when you ingest new documents into Lucene, those documents are not visible to searches until they've been digested, and the term of art in Lucene is committing. So once your new documents have been committed, then they're visible to the search. But that takes milliseconds to seconds for that to happen, and you really don't have any control over how long that takes. We actually spent a lot of time trying to solve that problem in DataStax Enterprise because we have a search based on Lucene there for text-oriented search, and we could not close that. We could not get that gap down to zero, which is what database users want. Database
They want
users
to be able
expect
to
when I've
read
inserted a
their right.
row, it should be visible in all my
Yeah.
indexes, no matter what shape my query looks like. So that was the kind of friction point number one, and I knew about that going into it.
Mhm, mhm.
But what I didn't know going into it is that the Lucene vector index specifically is a single-threaded design. So you can when you're building that index, you can only build it with a single thread, and it's not thread safe to query at all, except from the builder thread until it's finished. So that aligns with Lucene's philosophy around ingest and commit, but it doesn't align around what I wanted to do for Cassandra, which is have a vector index that as soon as you enter that row, you can see it, you can search for it. So the first thing I did was to rebuild that builder, that index builder, to be non-blocking. And so not only can I build it with multiple threads, but I can query it concurrently as it's being built. And so that was so when I said that the first version of Astra vector search was built on Lucene, it was actually built on that hacked up, new and improved custom fork of Lucene with the non-blocking index.
Yeah, so you're a contributor to Lucene now. I saw those commits go through.
Yeah, so I had a couple kind of byproducts of what I was doing that got committed to Lucene, but the actual concurrent index never did get committed.
Yeah, and it's in that single thread business. I mean, when you look at why it exists in Lucene, it makes a lot of sense in Lucene, but it does not make a lot of sense in a highly concurrent distributed database that needs to have a real time. Like developers expect to read the writes and within a reasonable amount of time. Or, and I think this is probably another part of it, is that your writes should not impact your reads for performance.
Yeah, and like I don't want to blow my own horn too hard here because I don't think this was rocket science, but uh, it it's I did some good work here where
You're
it
having a
scales.
lot of fun. I can see it.
I've tested this out to 32 concurrent threads. You go from one thread to two threads to four threads to 8 to 16 to 32, and every time you double the number of threads that are building it, the time to do the build goes down by half. So it's a very very scalable design. And what the I mean, like I nerd out on the technical part, like that was a fun challenge, but for users of Astra vector search and Cassandra vector search, what that means for them is that search doesn't slow down while you are adding new rows, which is actually an unusual property for a
And
lot
it
of these vector
sucks.
databases. So I
Yeah.
already called out PG vector. So let's keep going. Pinecone actually really struggles with this.
Yeah.
So if you have like a steady static set of vectors that you've ingested, like great, everything's fine and the sun is shining and birds are chirping and whatever. But as soon as you start doing concurrent inserts or modifications of those vectors, then Pinecone really struggles.
I want to give the every vector database that was built in the last few years a break, maybe like give them an out. Is that I feel like the use case at that time was some batch process creating a lot of embeddings and then dumping them into a place where they can be indexed and then later read in a very performant way.
No, you're right. And to the degree that like there's always a temptation as an engineer to build for the test, so to speak. And the big industry benchmark here is called ANN-benchmarks. You can find it on GitHub. They have a dozen data sets that are all standardized, and you can point your vector database at them. But the way that ANN benchmarks works is it's a single threaded it's a single threaded design, and it's split up into load my stuff
Right.
and then query my stuff. So there's no you can be the slowest design in the world at uh, ingesting while you are querying, and it doesn't show up in the benchmark at all because
Right.
that's not what it's designed for. so yeah, there's definitely a temptation to say, well, nobody's looking at how this works when I'm doing those concurrent operations, so maybe we'll leave that for later.
It reminds me of like when you could fit your data into memory and then do a benchmark on that. Like, like that.
Yeah, and
That's not a good test.
I remember writing, it must be 10 years ago now, like 2012-ish, where I got really frustrated at people benchmarking Cassandra with a for loop. Like I'll do one request and then I'll wait for it to come back and then I'll do another request and then I'll do another. Cassandra is designed for thousands and hundreds of thousands of concurrent requests. So yeah, it's super frustrating to see that like enshrined in the ANN benchmark that, oh yeah, it's just a single thread.
Yeah, well, it doesn't really. I mean, it's interesting if you're testing the indexing algorithm for one use case, and that's I think that's what ANN benchmarks does. Is it's like, hey, here's this algorithm with this very pure type of benchmark, but as many benchmarks go, it doesn't actually translate to application developers that are building stuff that needs to perform. Like
Yeah,
it's
I
not
mean
real world.
it's like in the Java world, right? You have I believe parallel GC is still the throughput champion. It will pause your application for multiple seconds while it does its garbage collections, but its throughput is amazing.
Yeah.
On the other hand, like there's a reason why the JDK team has spent years making ZGC production ready to bring pause times down to single digit milliseconds because that matters in practice. So yeah, I get it. Like there's a place for benchmarking the pure single threaded algorithm, but there's also a place for understanding that hey, in the real world, it matters if you can do concurrency.
Yeah. Well, and so back to and keeping on the theme of real world scale. I'm giving a talk right now on vector, and I talk about like if you it may work great on your laptop, but wait until you put it in production, right? So scale that's yet another problem, and one that we've been talking about for years, only from the beginning with Cassandra. So maybe you can talk a little bit about that, and I'll just prime the next question because I know they're related. Is the vectors that don't fit in memory, the ones that have to go to disk, like how do those two things play
Yeah.
together?
So like yeah, for scale, I've been saying for years that if your problem fits on a single machine in RAM, like it kind of doesn't matter what you use to solve that problem. Like you can use Redis, you can use MongoDB, you can use SQLite, like it doesn't matter
Right.
because it's just not a challenging problem domain. Um, so the same thing is true with vector search. However, the slightly different piece with vector search is that vectors are large, relatively speaking, relative to what the database world is used to optimizing for. Especially if you're using OpenAI Ada 2 embeddings, which are 1536 float 32, so that's about 6 kilobytes a piece. Like that's it takes 1 to 2 orders of magnitude less of those to max out your RAM than you're used to if you're used to dealing with integers or longs or a few of those together. Um,
And I'm going to flag that as your first shock of working with it. Those of you who have not worked with vectors yet, warning, that is a thing. I mean, these aren't just a single, this isn't a 32-bit number. These are massive. And per row, you get these. So this is why scale is a thing.
Yeah, and by the way, I'll throw out a recommendation. If you're not locked into an embedding implementation yet, you should be using the E5 family, which you can find on Hugging Face. The E5 standard and the E5 large both outperform OpenAI's embeddings for retrieval, which is what most people are doing here, while being smaller. And the E5 small or E5 small v2, even better, is a quarter the size of OpenAI's, and it's very, very close. It's like within 5% of the OpenAI relevance that you get out of it. So definitely
Gotcha.
recommend those, because like it's not just the like disk space is cheap. We'll talk about disk space in a second. Disk space is cheap, but CPU and GPU cycles are actually not cheap in the vector search space. You can max those out relatively easily, because what's going on when you're doing a vector search in your index, you're doing a whole bunch of comparisons between your query vector and what's in the index. And so if you have a query vector that's a quarter the size, then your search is going to be 4 times as fast, other things being equal. So it's in your best interest as an application developer trying to get low latencies to your customers to use a smaller embedding vector if that can do the job. But the question was, what do you do when your data set outstrips RAM? And so I mentioned that Lucene and by extension Astra started out using an HNSW vector search algorithm. And HNSW is what everybody starts with for 2 reasons. And like seriously, like if you name a vector database, well, actually PG Vector didn't start with it. They started with something else, but now they have HNSW. But if you name a vector database, odds are they have HNSW, and that's in most cases that's all they support.
Yeah.
And there's good reasons for that. The 2 very good reasons are HNSW is fast. It's faster than almost anything else, and it is high relevance.
Yeah.
So if you say, hey, HNSW index, find me the top 10 vectors that are closest to this query, you will get 7, 8, 9 out of the actual closest vectors just without much effort. Like you're not going to have to tune it. You're not going to have to explore your problem domain super hard. Like just out of the box, that's what you'll get. Whereas with most of the other alternatives to HNSW, you're going to get like 5 out of 10 out of the box. And so the relevance matters and the speed matters. And then one more thing that's actually really good for a database like Cassandra is that HNSW can be built incrementally, meaning I put my first vector in, I put my first 5 vectors in, I can search that. That is a searchable index with just 5 vectors, even if I'm inserting a total of 1 million or more. I can build it incrementally and search it incrementally, which is not a property that a lot of other options have. So those are the reasons why everybody starts with HNSW. The problem is, and this is, again, this is not a secret, this is not something we uniquely discovered, this is very well known in the industry, HNSW does use a lot of RAM for those indexes. And once you exceed RAM, then your performance starts to get bad very, very quickly, because unlike in a relational database, unlike with most B-tree indexes, there's no hot data set, there's no hot subset that you can say, okay, like that'll live inside the cache, and then everything else we can just kind of pretend it doesn't matter. Because every vector in your vector index there's some exceptions, but mostly you have an equal chance of needing to read any of those vectors during a query. So the property of not doing well once you exceed RAM really, really matters, much more than you would expect if your intuition, like mine, comes from other kinds of databases and other kinds of retrieval patterns. So that's the long way to explain why.
I don't think a lot of people know that, though. I think and I thought it was interesting because the Lucene HNSW, as I was reading through the issue that they created for it, the hierarchical network small world HNSW, it does multiple dimensions by design, but the Lucene folks decided to do one dimension. It's like, that's it. It doesn't do multiple layers. And I think that probably has a lot to do with memory. Do you think that might be true? Or
I'm not 100% sure what you're thinking of there because the Lucene HNSW absolutely does do multiple layers. So
I
backing up
you
for
said that
our
to me
listeners,
before.
backing up for our listeners, the problem that we're trying to solve with HNSW is, or with vector indexing is, I want to find the closest vectors to my query without exhaustively examining every vector in my data set. Like, because if I'm having to do a linear scan for every search, like I run out of gas somewhere in the 100,000 or million vector range. It's just too slow. And so what HNSW proposes is, um, it's actually an extension of an earlier thing called NSW, Navigable Small World, where NSW says, hey, let's make a graph of our vectors as we add them to the index. And I'll look at each node in the graph, and I will set as its edges to other nodes the vectors, the other vectors that are closest to it. And then the hierarchical Yuri, whose last name escapes me, but the guy who created HNSW, he said, "Hey, like this is great, but it has worst case properties that are not desirable. Like if it's relatively easy to end up in a degenerate NSW where you're actually getting linear search times again." So what he added was the H part, the hierarchical part, which said every 10% or so of my vectors, I'll put those in a new graph layer that sits above the first one. And so that's going to have just a smaller pool of candidates. And what that means is that my edges between nodes are going to be longer. And so traversing each edge moves me a farther distance in a single traversal. And so I have my base layer, and then the next layer is 10% of that. Then my next layer above that is another 10%. So it's 1% of the original. Then the third layer is 0.1% of the original. So it's got this kind of skip list property where you start at the top layer, find the closest match, then go follow that to the next layer, because each layer down is a strict superset of the one above it. So you follow that down to the next layer, find the closest one there, then go down, find the closest one there. And so you kind of drill down to the right area in logarithmic time, which is what you want out of an index.
Well, I'm going to stand corrected, by the way. The initial HNSW was a single layer, but
Oh yeah, I think you're right about that. Yeah,
yeah,
like the
and I
original
found the
patch
ticket.
posted. Yeah.
Yeah, so Lucene 10,054, just, I want to make sure I quote my sources. Maya Sharapova made it multi-layer because the single layer sucked. So
Yeah, yeah,
there you
it
go.
does, because you only have, if you're in a single layer, then you have, well, the biggest problem is that you're not traversing. If your entry point to the graph is not close to your query that you're looking for, it takes you a long time to navigate to the right neighborhood because you don't have those longer edges that you get with the hierarchical layers.
Yeah. And I should add, everyone who's watching live right now, please ask questions. I mean, we're sitting in here talking about all kinds of neat, cool stuff, but you should feel free to ask questions. It's you've got clearly you got someone here that can answer the most incredible questions, like how many layers HNSW has in Lucene. But yeah, feel free to answer or to ask questions. Sorry. So back to you there, Jonathan. You were
Yeah,
going somewhere.
so I mentioned that we got a little bit deep on the HNSW, and I made a claim earlier that you can't cache like a hot and a cold data set with a vector index. What you can do with HNSW is you can say, okay, I'm going to cache all but the bottom layer. Or if I'm really sensitive to memory use, I'll cache all but the bottom two layers, which get me like I'm caching 10% or 1% respectively. The problem is that once you get to that bottom layer, you're still in a world of like, I'm just doing random IOPS all over the place and my performance sucks. So being able to cache those top layers, yes, you can do that. And yes, we did. but it's not enough. And so what I started looking for, basically as soon as we released the HNSW as
Oh,
beta,
I know where you're going. This is great. Keep going.
was to look for an alternative that would work better when data sets get larger than memory. And so the two that are, I think, the state of the art right now, they're actually both from Microsoft Research. Um, and I don't actually know the details of like which parts of Microsoft created which one. But the first one is called SPAN, SPANN, and the second is called DISKANN, DISKANN. And I'll let reading SPAN be an exercise for the reader if you're interested. It's actually a really interesting design. And it's completely different from HNSW and DISKANN because it's not a graph design.
Mm.
And so while that's an interesting approach, I decided to build the next version of Astra Vector Search on top of the DISKANN design because it is also a graph index like HNSW. And so the distance between what I had and what I wanted to get to was relatively small. And so what I've done is I've taken, because this is starting to get farther and farther away from what Lucine's implementation looks like, I actually extracted the graph index into a new standalone project called JVector, and I built DISKANN
There's your link.
in the JVector project.
I knew it was coming. I was ready for it.
You were ready. Yeah. So if you follow the link, you'll see some preliminary benchmarking results versus Lucene. What I did was I built a index of 100 million. Sorry, I'm mixing my. So I benchmarked 100 million vectors of the E5 family, E5 small v2, like I recommended earlier from Wikipedia. But that's not the graph that's on the front page of the JVector repo.
By the way,
on the
that's
JVector repo
all of
page.
Wikipedia, right?
Yeah, actually, that's basically all of Wikipedia chunked into roughly sentence-sized pieces and embedded. But yeah, what's on the repo front page is a comparison with the deep 100 million data set. And so that is about a 60 gigabyte index once you've built it. And so I built the index on a large EC2 machine, and then I downloaded it to my MacBook Air with 24 gigabytes of memory. So roughly I've got about a third of the memory on the MacBook as the size of the index. And so even before you start taking away things for Mac OS and for the JVM, it's not going to fit. And so what you see is that JVector is outperforming Lucene by a factor of about 4 on that data set. And that graph's going to be updated because we're still optimizing JVector, and it's just getting better.
Yeah, well, I mean, that's the thing. If you follow that link, there's some some very compelling graphs in here. But one of the things that you mentioned earlier was around this going from single thread to multi-thread, and I also SIMD, which for Java folks, SIMD has been kind of hard to get to, but now you can, which single instruction, multiple data, and that's basically using the way that architecture of modern chips to not have to reload data directly from memory all the time. You use a single instruction and just pipelines it all through the same instruction. You get tons and tons of performance out of that, not using a GPU, by the way. But maybe you could talk a little bit about that, like that multi-thread, like what you got out of it, before and after. And then
yeah. Okay. So,
yeah.
So some of what you're talking about isn't actually unique to JVector. So Lucine's doing the SIMD stuff as well, for instance. And so, but for people who haven't looked at that, or who have looked jealously at C++ and what you can do there, starting in, I want to say Java 17. Actually, no.
20.
I think it might even have been Java 14.
Oh,
For
14?
for several releases now, you've been able to do SIMD using Java, but it's an incubator feature, which means that you have to opt into enabling it, and it's subject to change. And so it's actually changed. It actually has changed several times across the releases, but it looks like it's starting to stabilize because in Java 20, I believe that our Java 20 implementation runs unchanged on 21. Uh, but
That's Panama you're talking
yeah,
about?
yeah. So there's an implementation of that lets you use AVX or whatever the AArch 64 equivalent is, and do dot products faster, do sums of floats faster, because you're taking advantage of the hardware to do what it's supposed to do.
Yeah.
So that's not, like I said, that's not unique to JVector, although some of the things that we are doing in JVector are unique. So let me back up a second. So I said that the JVector implements disk-INN, which lets us serve larger than memory indexes much faster than an HNSW index. There's two Well, there's one main component to that. There's another piece of disk-INN that I won't cover. The main component to dealing with larger data sets is that disk-INN just says, hey, we're going to quantize the vectors and store those in memory. So quantizing means we're basically doing a lossy compression on your vectors. We're basically JPEGing your vectors. And so that means that I can keep those in memory at the price of 1/8 or 1/16 of their original size. And so what disk-INN does to reduce the relevance impact or the precision impact, it does two things. First, building the graph is always done with original precision, and then what you can do is you can search if you're searching for 10 vectors, you can look for more. You can look for the 20 closest using those quantized, lossily compressed vectors. I can look for the 20 closest and then only sort those 20 by the original vector. And so what disk-INN does is when it's storing the graph on disk, every node, it stores the original vector and then the neighbors of that node. It stores those as a group. And so when I touch that node during the search, I'll just save the original vector for later. And when I'm done with my search, I'll go through those original vectors and use those to resort and get the actual top K that the query asked for.
And that actually is a very interesting point about the top K, which is the relevancy. I've said this a few times, like, for database folks out there, we've always been worried about throughput and latency, but the third
Mhm.
dimension that you need to consider with vectors is this relevancy. And it seems like, I'm looking at the graphs in the project, it seems like relevancy is actually better because of the way this works. Does that seem right?
So
I know you're
this
gonna be.
is
Oh, this is great. I got you a little twitchy here. Okay, so what is it?
so if you do a quantized search with exactly the same number of nodes traversed, then you will get worse relevancy.
Right.
But doing that faster comparison of the quantized
Mm.
vectors means that I can afford, given the same time budget, I can afford to look deeper, which will actually increase my relevant past where it was originally. So I would say that having a better implementation lets you choose whether you want to spend that savings on, do I want more throughput or do I want better relevance?
Right. Yeah, I mean, and that I think that's going to be something we as an industry, as users, are going to have to just really. This is just a competency we're all building. It's like, oh, what? How do I measure relevancy? Why is it important? And that's a hard thing about ANN. It's like horseshoes, close counts, but how
Yeah, it
close?
does. Yeah.
Yeah, you just don't get an exact match. That's not the point. Um, but you don't want something that's just so off in left field that you're like, why are you even giving me this result?
Yeah. And so this is interestingly, this is kind of an open area of research of how do you apply GPUs to make vector search faster. So NVIDIA, has an implementation of vector search that runs basically entirely on the GPU, but that means that your data set is limited to stuff that fits in your GPU, and it also means that the thing about GPUs is they are super cost effective if you can keep them 90%, 100% utilized. But if your GPU is like 10% utilized, then you're just paying a lot of extra money for performance that you're leaving on the table. So I believe, I'm not 100% sure, but I believe that it will continue to be the case that GPUs for vector search mostly do not make sense, especially for scenarios like what Cassandra is designing for, where my data set is dynamic. It changes as rows get inserted, as rows get deleted, and we need to handle both of those conditions. It's possible that if you've got a data set of 25 gigabytes of vectors, like the deep 100 million data set, which is, by the way, those are vectors that are 96 float 32s large, which is smaller than almost any text embedding out there. Um, so you can get a lot more into 25 gigabytes when they're tiny vectors. But if you've got a static data set like that, then yeah, maybe it makes sense to use a GPU search if you're saturating it constantly. But otherwise, probably not. Where I was going with this was one of the things that we did.
But wait.
Uh, One of the things that we did with this was my colleague Sebastian Estevez built a data set generator using GPU. So one of the reasons why you only have a dozen or so data sets that everyone uses to benchmark their vector search with is that it's really computationally expensive to find the closest 100 matches to a query vector when you have 100 million vectors to scan, to find, to determine what the actual, we call it the ground truth, what the ground truth results should be. And then that gives you a yardstick to measure, oh, how many did I get correct? You need to know what the actually correct values are to see how close your approximation got. And so Sebastian built a tool that computes those ground truth values on the GPU. And so now we have,
That's some good stuff right there.
yeah. So we've got a 100 million, a 1 million, and a 4 million vector data set from that subset of Wikipedia vectors where we know the exact answers.
Yeah, next stop at 1 billion. But I mean, like all Wikipedia is 100 million. What's next? Well, maybe that's we've been talking for 45 minutes. I can't believe this, but this is great. I'm gonna try to wrap this up with so here we are today, point in time. Today is September 20th, 2023. Just to mark time, epoch. But like what are you thinking? This is an arms race right now. I mean, vector is not a differentiator anymore. It's every database is doing it. But there are things that Cassandra can do, I think, better than any database for sure. But what's driving you? What are you thinking about in the future? What do you want to try to achieve?
So the first thing is to just make our implementation the best that we possibly can. So we've been working on this for 4 months, 5 months now, and We've got the basics there. We've got larger than memory data sets with disk A and N. We've got composing with other query predicates. And by the way, this is something that you should be looking for in a vector database. Like you need to be able to do both traditional databasey things and also vector search and combine the two. So if you're talking to a vendor who's like, oh yeah, we do the vector part, keep using your existing database for everything else. Well, that's the classic. Okay, now I need to keep these in sync. And what happens when the replication pipeline breaks? How do I rebuild it? Like it's a mess. It's yeah, you don't want to go there. It's like back when you were stitching Lucene and Oracle together to get full text search. Don't do that. So with Cassandra, you can do the vector search parts, and you can also restrict the vector search by your other indexes. But you can also do queries and indexed searches that don't involve vectors, because sometimes your application needs to do that. Like just as a really simple example, like everybody, like the hello world of retrieval augmented generation is to do a chatbot that knows that about your documentation. And so you do a vector search to find the doc pages that are closest to the query that the user asked. And then you pull that back and give it to the large language model as context to answer the question. But even in that hello world, like the vector search is just part of what you need from your database, because you also need to be able to say, hey, database, what are the last 10 messages that we sent back and forth? And that's not a vector query. That's just a standard timeline query for the database. So you need to be able to do both.
Yeah, yeah. Then I do worry that we are, well, I'm not particularly worried. I've been around long enough. I know where this is going. We're all POCing right now. We're all looking, and the chat bot is the POC. That's the hello world of Gen AI right now. Everybody's trying to add a chat bot to whatever they have. But I think quickly, and this is the where things are headed so quickly, is agents, and that's when things are going to get really interesting, because that's going to need high concurrency, a lot of distribution, and then scale, because multimodal everything. It's not just a bunch of typed in words from a human. It's going to be images and everything else. But yeah, I think of scale as such. It's going to be the problem that most vector databases are going to have because of users.
Yeah, I think that's right. And not just the scale in the, hey, I'm going to ingest a larger static set, but scale in the sense of it's changing, it's dynamic, and I need to be able to deal with that.
Right, right. Well, wow, man, 50 minutes. We've done good here. I don't see any questions. I think that probably a lot of people are like trying to drink from the fire hose right now. That's okay. Um, feel free if you see this after the fact and you want to put a comment in, do it. We'll be there. We'll answer those questions after the fact. Jonathan, I really appreciate spending the time here with you. I I almost got the bends. We went on such a deep dive. This is great.
Thanks, Patrick. It's been fun.
Yeah. So thanks everyone for being here today.
Bye.